Hi folks, welcome to our next installment in the Bode plotting series. This session is going to deal with plotting real poles and zeros, which are also called simple poles and zeros. So a simple zero is going to have the form h of s equals 1 plus s over omega naught. Omega naught is a constant, so that's going to be called the break or corner frequency. And you'll see why we call it the break or the corner frequency in just a moment. So if we substitute in j omega for s, we're going to have h of j omega equals 1 plus j omega divided by omega naught. All right, so now we can look at the magnitude of that. Okay, so the magnitude of h of j omega is going to equal the square root of the quantity 1 squared plus omega divided by omega naught squared. All right, so that's going to be the gain expression. Okay, so next we're going to talk about the phase, and the phase portion, the angle of h of j omega is going to, well, we know that's going to be, this is a complex number, so that's going to be the arctangent of omega divided by omega naught divided by 1. So it's going to be the arctangent of omega over omega naught quantity divided by 1, which is just omega divided by omega naught. Okay, so that's going to be the phase expression. So now we want to look at what happens as we vary omega across some frequency range of interest. All right, so we have three cases to deal with. The first one is case 1, and that's going to be omega is much smaller than omega naught. So what that gives us is that omega divided by omega naught is going to be, we're going to treat it as nearly 0. And if that's the case, then the gain expression is going to be the square root of 1 plus something that's close to 0. And the square root of 1 is 1. So the gain will just equal 1 unitless, which means the gain in dB is going to equal 0. Right? So that's going to be 0 dB when omega is small compared to omega naught. So next we got to deal with the phase, right? So we know what the gain expression is. What's the phase going to be? Well, if we go over here and we look, we have essentially 0 in here when omega is much smaller than omega naught. So the arctangent of 0 is going to be 0. So that's going to tell us that the phase equals 0 degrees. Now the next case we have, case 2, is when omega equals omega naught. And so in that situation, we have that omega divided by omega naught equals 1. So now we have our gain is going to be 1, the square root of 1 plus 1 squared. Right? So it's going to be our gain equals 1 plus 1 squared, or just 1 plus 1, and that quantity square rooted. So it's going to be square root of 2, and so our gain in dB is going to be 20 times the log base 10 of the square root of 2, which is going to be plus 3 dB. Okay, for the phase, in this case, we're going to again have omega divided by omega naught. So omega divided by omega naught equals 1. The arctangent of 1 is pi over 4, or 45 degrees. So the phase equals 45 degrees. Now, the next case to look at is going to be case 3. And that is when omega is much larger than the break frequency. Okay, so when omega over omega naught is large, then omega over omega naught squared is even larger. And if we add 1 to it, we're really not changing it very much. So we're really going to have something that looks like omega over omega naught squared, and then we're going to square root it, which is just going to look like omega over omega naught. So the gain, unitless, is going to approximate omega divided by omega naught. In dB, we're going to have 20 times the log base 10 of omega over omega naught, which equals 20 times the log base 10 of omega minus 20 times the log base 10 of omega naught. Omega is the variable that changes with frequency, and omega naught is fixed. So we're going to have something that changes. It's going to increase by 20 dB for every decade increase in omega, just like the kind of thing we had with a 0 at the origin. And then we're going to subtract a constant value. And in a moment, we'll get to what that means. All right, so what happens to the phase? Well, in this case, we're going to have something that is unbounded. So the arctangent of something that can just get increasingly large is actually going to essentially max out at the phase is going to go to plus 90 degrees. All right, so we're going to have 0 degrees early on, 45 degrees in the middle, and 90 degrees at high frequency. The gain will be 0 dB. It will transition to plus 3 dB at the break frequency, and then it will roll off, or I'm sorry, it will grow beyond the break frequency. So what do I mean by that? So the first thing we're going to have is our gain axis. And just like before, our frequency is logarithmic frequency. We'll put our break frequency right here. We're just going to say that's omega naught. All right, so I'll call that omega naught. And then and this is our gain, is going to be, the scale is going to be in dB, right? So gain in dB. And so now let's look, first of all, we're going to do the straight line approximation. So we're going to say for low frequency, you know, if we just pick a point here, we're going to be at 0 dB. And we're going to say that that line is straight at 0 dB all the way out to the break frequency. So I'm just going to draw that as a straight line all the way to omega naught. And then at omega naught, what I'm going to do is I'm going to start increasing at 20 dB per decade. And you say, well, why does that occur at omega naught? Well, if you recall, a 0 at the origin always cross through 1 radian per second. Well, it turns out if you move the curve down by this value here, that's characterized by this negative 20 times the log base 10 of omega naught, it will slide that over so it crosses at omega naught radians per second instead of 1 radian per second. So what will happen is our straight line will then increase at 20 dB per decade off in this direction. Okay, so that's our straight line approximation. So this is plus 20 dB plus 20 dB per decade. Okay? Now, it doesn't precisely do that, because if you recall, we looked at the gain in decibels at the break frequency was actually plus 3 decibels. So really what's going to happen is our curve is going to start close to 0, and it's going to move along like this, and it's going to actually miss this corner by a little bit, and then it's going to go asymptotically toward that red line. So it's going to be very close to parallel to the red line here. It's going to make a little more of a curve instead of an angle here, and then it's going to asymptotically approach the red line there. And it turns out the difference between here and here is 3 dB. So that height is going to be 3 dB, approximately 3 dB. Now let's talk about the phase curve. Okay, I'm going to put 0 degrees down here. So this is 0 degrees, and again, this is our phase in degrees. All right, and I'm going to go ahead and mark this as 90, and I'm going to mark this as 45. And so, and again, this is our log omega logarithmic frequency scale. And I'm also going to go ahead and mark omega naught on our axis. And then I'm also going to put a mark at what would be 10 omega naught. And I'm also going to put a mark at 0.1 omega naught. Okay, so 10 times omega naught and 1/10 of omega naught. And I better label omega naught here. Okay, so now we can still look at straight line approximations. All right, so I'm going to go ahead and use my red color for that approximation. And I'm going to right at low frequency, our phase is 0 degrees, so I'm going to draw a 0 degrees straight line from the origin of my axis, whatever that happens to be, out to 0.1 omega naught. And then I'm going to go up, right, and just to make sure, help me with drawing a little bit, I'm going to mark this as a dotted line here at 90 degrees. And then I'm going to draw another straight line that is parallel to the omega axis at 90 degrees, and that's going to begin at 10 omega naught. Okay, so it's going to be right here. And then what I'm going to do is I'm going to connect those two lines together with another straight line. So I have 3 straight lines, one that goes along at 0 degrees up until 0.1 omega naught, and then it breaks and moves upward until we get to 90 degrees, and that's going to occur at 10 omega naught, and then the line is going to be flat again. And it also turns out that if we look at omega naught, that line should cross at 45 degrees. And that's what it should be, because we have 45 degrees right here. So again, we're at 0 degrees at low frequency, 45 degrees at the break frequency, and plus 90 degrees when at 10 times omega naught, or at high frequency. And then it basically stays there from that point forward. Now, that was our straight line approximation, which is generally good to sort of eyeball what's going on. But in reality, we don't have these little corners in this. So really what we're going to have is something that looks like it's going to come in from the low frequency, and it's going to kind of S through this. So it's going to smooth out that corner a little bit, go through there. I don't like that drawing. Let's try that again. There we go. Now I'm going to move this along here, and I'm going to come up like that. So there, that's what it's going to look like. It's going to be a smoother curve than our straight lines. But again, the straight line approximation is a very good approximation to what we're trying to get at. So this is the Bode plot of a simple zero. Okay, so now we're going to look at a simple pole, or a real pole. And it's going to have a transfer function that looks like h of s equals 1 over 1 plus j omega over omega naught. Okay, so it really is just the reciprocal of the simple zero. Okay, so we're going to look at the gain expression. So the gain is going to be 1 divided by the square root of 1 plus omega divided by omega naught squared. Okay, so that's probably not a surprise. It looks just like the reciprocal of what we had for the real zero. And then the phase expression is going to equal, well, it's going to look a lot like what we had before, except now the angle is going to be negative because we're going to be dividing by something that looks like omega over omega naught divided by 1. So we're going to have the negative arctangent of omega over omega naught. All right, so, and we could put the negative inside if we like. Turns out that the arctangent function will support that. So again, we want to do what we did before. We want to look at 3 cases. So the first case, so case 1 is omega is much smaller than omega naught. And from that, we have that omega divided by omega naught is approximately 0. So if we look at the gain, it's going to be 1 divided by something that looks like the square root of the quantity 1 plus 0. And so that means the gain is approximately equal to 1. And we know that that is 0 dB. All right, and the phase, what we're going to have there is negative arctangent of something that looks like it's close to 0. Well, the arctangent of 0 is 0, so we have negative 0. So the phase is going to be close to 0 degrees for low frequency. All right, so next we want to go to case 2. And that's when omega equals omega naught. All right, so notice, by the way, case 1 looks just like case 1 for the simple 0. We're at 0 dB and 0 phase. So, but now we're going to see something different happen here. Case 2, we have omega equals omega naught. So that means that omega divided by omega naught is well, not approximately 1, it's actually identically equal to 1. Okay, so now we have something that looks like 1 squared plus 1, so that quantity 2 square rooted, and then we reciprocate it. So the gain is going to be the square root of 2, and we know, 1 over the square root of 2. And so that's going to turn into negative 3 dB. Actually, negative 3.01 something something, but it's going to be negative 3 dB for our intents and purposes. All right, and then we also want to look at the phase. So the phase is going to be the arctangent of 1. It's going to be the negative arctangent of 1, which is going to be negative 45 degrees. Case 3, and that is omega much larger than omega naught. So in that case, what we're going to have is, just like we had the 0 was dominated by the, right, if we pull this back down here, we look at the 0, this was in the numerator, so this term dominated, and it's going to dominate in the denominator also, but that means that the denominator is going to get small, and it's going to get small fast. Okay, so the 1 really is inconsequential once omega is sufficiently larger than omega naught. So we're going to really look at something that looks like a gain of 1 over the quantity omega over omega naught. All right, so what is the gain in this case? Well, we know that omega over omega naught is going to be getting increasingly large, and the 1 becomes inconsequential at that point. So really we're going to look at something that looks like 1 over the square root of the quantity omega over omega naught squared, which is just going to be 1 over omega naught. So the gain is going to approximate 1 over omega naught. So if we compute that gain in dB, I'm going to give us just a little bit more room here. It's going to look like 20 times the log base 10 of omega naught minus 20 times the log base 10 of omega. Okay, so this is a fixed value, and this is the value that's changing with frequency. And so we'll see this whole thing is going to be a fixed value. That's just going to move the curve up slightly, but the curve is going to decrease at negative 20 decibels per decade in frequency. All right, so, and for the phase, well, there we're going to end up using the same argument as before. As omega over omega naught goes toward infinity, then the arctangent is going to be 90 degrees, but we have this negative out in front, so that means our phase is going to go to negative 90 degrees. All right, so now we're going to plot these. So first we're going to look at our magnitude plot. Okay, that's our logarithmic frequency, and this is our gain in dB, and we'll go ahead and mark omega naught on here. I'm going to put it up here, so that's where omega naught is. Okay, so now we're going to use the rules we have that said at low frequency we're going to be at 0 dB. So first I'm going to draw the straight line approximation. It says we're going to move out here like this. Once we get to the break frequency, I'm going to say that we're going to move downward at 20 dB per decade. Okay, so the slope here is negative 20 dB per decade. All right, and obviously we know really that's not what happens. We actually have a curve here because we actually got to encounter our negative 3 dB point at omega naught. So we're going to come in here with a curve here that kind of breaks around this corner. And so there's what the actual trace is going to look like. So if you recall, that looks like a low-pass filter, and I'll talk a little bit more about that in just a minute. Looks like the magnitude response of a low-pass filter, that little RC filter that we talked about in class. So now if we look at the phase, to do the construct here, again, we've got our frequency in its logarithmic and our phase in degrees. Phase in degrees. And so this is 0 degrees. And I'm going to put negative 90 down here because I know where I'm headed. And I'm going to go ahead and mark omega naught right here. And I'll go ahead and mark that, omega naught. And then we'll also have 0.1 omega naught, 0.1 omega naught, and 10 omega naught. So those are separated, omega naught, separated a decade apart. And we're going to have 3 straight lines. I'll go ahead and draw a dotted line here to help me at negative 90. And then I'm going to pick my color here for my straight line approximation. So I'm going to be 0 degrees until I get to 0.1 omega naught. And I'm going to be at negative 90 when I get to go from 10 omega naught and higher. So I'll go ahead and draw those 2 horizontal lines in there, and then I will just connect them. Okay, again, that's my straight line approximation. And I'm also going to see that I should go through, omega naught should be negative 45 degrees. Right, because that's what I said I have right here. Okay, so now the actual curve is going to be a little more S-like, just like in the previous case, but now we're going in the negative direction instead of the positive direction. So I'm going to sort of cut off this corner here I'm going to snake through here. Boy, I have trouble doing this, but you guys know my artistic skill. So we're going to cut off through here and cut off through there. So that's essentially sort of what our phase response is going to look like. So it's asymptotic in the low frequency with the axis, and it's asymptotic in the high frequency with negative 90 degrees, right? So this would continue tapering off toward negative 90. It won't pass it. And it will be negative 45 degrees at omega naught. So that is the Bode plot for a simple pole or a real pole. And it really does look like the Bode plot for a simple zero, just turned upside down. So you want to keep that in mind. All right, now I want to say one more thing about, I mentioned earlier this RC circuit. So if I just go out here and say I'm going to write the expression, if you recall, we had our RC circuit transfer function looked something like H, I'll write it as J omega, equals 1 over J omega RC plus 1. Okay, that was our simple RC circuit. Just to remind you, it looked like this. Right, so we had Vn over here, V out over here, we had a resistor, and we had a capacitor. Okay, so now that's not quite, if you notice, it's not quite in the form that I explained earlier, right? So what I need to do is do a little bit of algebra on this to come up with the form that I'm interested in. Okay, so I can say that this is actually going to equal H of J omega equals 1 over 1 plus J omega divided by 1 over RC. Okay, that's going to be the same expression. And so what we would find is, for this particular case, the break frequency is going to be omega naught equals 1 over RC. And from this, what we can see is then we can tune the break frequency of our low-pass filter by, if we know what we want the break frequency to be, then I can choose, let's say, R, and then I can just compute what C needs to be, right? Because the capacitance value is going to be 1 over omega naught times R. Alternatively, I can pick the capacitor and I can solve for R. So I would have R equals 1 over omega naught C. So I have some flexibility, but I'm essentially going to end up with a simple low-pass filter that has a particular break or corner frequency. And in this case, we'd call it the cutoff frequency. What does that cutoff frequency actually mean? If you recall, we have H of J omega equals 1 divided by 1 plus J omega over omega naught. Okay, so, and that led to the gain of H of J omega equals 1 over the square root of 1 plus the quantity omega over omega naught squared. Okay, so at the break frequency or the corner frequency or the cutoff frequency, if we want to call it that, we know that omega equals omega naught leads to H of J omega equal 1 over the square root of 1 plus 1 squared, which equals 1 over the square root of 2, right? We talked about that. And then if we take 20 times the log base 10 of 1 over the square root of 2, that gives us negative 3 dB. Okay, so this unitless ratio here is actually going to be V out over Vn, right? That's V out over Vn. And we know that V out over Vn quantity squared is proportional to power out over power in, right? So if we take 1 over the square root of 2, quantity squared, that's going to be 1/2, which equals P out over P in. Okay, so 1 over root 2, when we talk about a voltage ratio, or -3 decibels, corresponds to P out over P in equal 1/2, which is the half power frequency. So typically the cutoff frequency for a filter circuit is defined as the frequency at which the output power is 1/2 the input power. And what that means is the output voltage is going to be 1 over root 2 times the input voltage, or 0.707 times the input voltage. So that's where that comes from. So anyway, I hope you found this useful. The last segment that we're going to have before we work examples is going to be the quadratic poles and zeros, and that's going to involve some complex terms and damping and things like that. So anyway, have a good day. Look for the next lecture. Thanks.